Okay, our title is MEMS thermal sensor. The operating principle of the design MEMS thermal sensor is based on an infrared temperature sensor that can measure target surface temperature without touching by receiving radiant heat from the object with thermophile elements. Below is some of the thermal equations that can be used as shown below, which are thermal conductivity equation, heat equation, and sensitivity equation. The sensitivity equation of a MEMS thermal sensor indicates the percent change in measurable output for a given change in temperature. We can calculate the sensitivity of a resistant thermal by multiplying the resistor of the RTD at the reference temperature, which is R0 by the temperature coefficient of the resistance, which is alpha. Here is a deformation of our MEMS thermal sensor. We notice that it grows from a number close to 0 here, which we had a remote displacement, and as we can see that the whole model is growing away from this point if it is animated. As we can see, the blue is the cooler parts where it grows toward to red, which is the hottest temperature part.
Okay, this is the top view layout of our design in MEMS Pro simulation, where the purple color is the aluminium and the red color is the silicon nitride. We use poly 1, metal 1 electrode as our layer for this design. For material database table, we use the same elastic moduli, position ratio, and density from this table. The material that we use in this MEMS Pro design is silicon dioxide, polysilicon, aluminium, phosphorus, boron, and silicon nitride.
This is our process definition and 3D model in MEMS Pro. Okay, the first step we substrate the wafer, and then we implant the silicon nitride, silicon dioxide. And after that, we deposit the nitride and we deposit the silicon dioxide. After that, the step number 6 is we etching the silicon nitride, silicon dioxide. Next, we implant the phosphorus and etching back the silicon dioxide. After that, we deposit silicon dioxide. We implant the boron, and the next step is we etching the silicon dioxide and we deposit aluminium. Okay, step number 13 is we etching the aluminium, we etching the silicon nitride and silicon dioxide. After that, we etching the silicon dioxide, we implant the silicon dioxide and we deposit the aluminium. After all the process that we do in MEMS Pro, we have get the final 3D model, which is this figure. And we can see that this is not meet our requirement, but this is our final cross section.
Okay, for analysis system, the thermal analysis is followed by linked structural analysis. The purpose is to transfer the temperature that result into a static structural analysis where we drop it into the solution branch so that we are using the same material, same geometry, same model, and same meshing. Also, the purpose of doing this is to bring temperature over to the identical mesh. Refer to our geometry figure. As we can see, the geometry has been done by using design modeler instead of importing it from the MEMS Pro IGS file. For the input and boundary condition, we have applied thermal condition and temperature as an input to the two materials, which are aluminium and silicon nitride.
This is our result in ANSYS solution. So in this picture, we can see the parameter of total deformation versus temperature. Total deformation is output and temperature is input. Total deformation will increase along the temperature. Okay, so this the next graph is total deformation versus condition versus thermal condition. Total deformation will increase along the thermal condition, and the third graph is temperature versus thermal strain, and the fourth is also temperature and thermal strain, but with different temperature, which is 22 degrees Celsius and 40 degrees Celsius. Okay, for thermal strain and temperature, from ANSYS simulation, when the thermal expansion coefficient increase, the thermal strain also will increase. Based on the graph, we can observe that if the temperature increase, the thermal strain will increase too, but the rate thermal strain increase depends on the thermal expansion coefficient.
Okay, for the MEMS thermal sensor for campus sustainability, the word thermal is assigned to describe a specific kind of energy. Thermal energy is produced by heating up molecule and atom until they move fast enough to collide into each other. By using a thermal sensor, we can use it to detect the thermal in the campus. For example, we can use this thermal sensor to detect the thermal in the laboratory because the laboratory is a hazard place for students where it's all dangerous material are placed. So by having thermal sensor, we can take a precaution to avoid something bad happening.
Okay, here is a MEMS thermal sensor for campus sustainability for United Nations Sustainable Development Goals, and we choose three, which is affordable and clean energy. Second is responsible consumption and production, and the third is sustainable cities and communities. Energy management is a global environmental challenge. Improper energy management will create numerous environmental issues such as shortage electricity, malfunction, electronic device, and lifestyle problems. A smart energy management is proposed by utilizing a MEMS thermal sensor. The smart solar system will create higher efficiency in terms of resources and costs associated with keeping the campus generated electricity by using the natural resources energy such as suns. Okay, next slide.